All right. Welcome to day 64, the LeetCode medium. We have the word search problem. And so we are given an n by n 2D grid of characters and a word as a string. And we need to determine if the word can be constructed from letters of sequentially adjacent cells. Cells are considered sequentially adjacent when they are neighbors to each other horizontally or vertically. The function should return true if the word can be constructed and false otherwise. And this is a very simple illustration of what we're going after. So educative, can we form the word? Yes, you can see how it works. So true, it can be found. Dynamic, no, it cannot be found. Warrior, oh, it's worth noting, right? This n doesn't complete it. You can't jump like this. You can only go up or down, up or vertically or horizontally, not diagonally. Warrior, yes, it exists. So yeah, that's the problem statement. And now we are evaluating the backtracking pattern. So that's what the solution involves. So we need to traverse all the elements of the grid. The sequence of letters that combine to make a word can be found starting from any index in the grid. Therefore, we need to find that word in all possible directions starting from a particular index. However, what would we do if we learned that the current path should not lead to a solution? And what do? We backtrack. We move backward from the current index and resume the search for the required word along one of the other possible paths. So traverse all possibilities to find the specific word without using the extra space needed to keep track of the visited or non-visited status of the cells. So we're looking for educative. We start from E. So we start here, mark it as visited, and call backtracking. D, okay. X is wrong, so you go right, X is wrong. So we check it down, and so on. So the solution is going to use depth first search. For each cell of the 2D grid, we have 4 paths we can take next. If the chosen path is incorrect, we backtrack and choose a different path until the word is found or all possibilities are exhausted. We can implement the depth first search algorithm using a recursive function. Now, even though it's typically associated with trees or graphs, we can apply it to the concept of connections between nodes so far we find it in any data structure. So in the 2D array provided as input, we see that each character located at cell ij is connected to its 4 potential neighbors, each addressable as cells I plus 1j, as a character below, I negative 1, j character above, j plus 1, character to the right, j negative 1, character to the left, in this case. And in graph terminology, we say that each cell in the input grid has a minimum of 2 and a maximum of 4 edges. Fairs. So apply depth first search to each cell of the grid, check for the base case in the depth first search function, and it occurs when we have matched all characters in the word individually, indicating that we have found the whole word in the grid. If this is the case, we have no more letters to explore in the word, so the length of the word becomes 0. Therefore, we return true. So basically, if you followed the series so far, we have to have a terminating condition in our recursion. And in this case, it's when we're done evaluating all the words. So word.length is equal to 0. Now we get into the real work, actually. You have to check if the current cell is a valid candidate for the next character of the word. So we're checking it if the row and column indices are within the bounds of the grid, right? So that's in line 20 to 24, that's over here. So the row is not less than 0, right? Because that's outside the grid to the left. And so if it's less than 0, bad times. If it's equal to grid length, rather off by 1 error, because you're indexing grid length, the maximum is grid length minus 1. Same with the column, same with the column length for a particular slice of the grid. And then also if what we're evaluating, the letter we're evaluating in the grid is not equal to the particular word that we're evaluating at this time. So that's what that's saying. Oh yeah, dimension line 25. If the character itself matches the next character of the word. So if any of these conditions are not satisfied, we cannot proceed with the current cell and return false to backtrack and explore other paths. Okay. Now after the current cell is, after ensuring that it's not out of bounds and it contains the next character of the word, we mark the cell by visited by setting it to star. Then we iterate over the 4 possible choices up, down, left, right, left, and call the depth first search function recursively with the updated row and column indices and the remaining portion of the word. For each possible choice, we check if the recursive call to depth first search returns true. If the call returns true, indicating that we have found the word, we return true. If not, we will continue the loop and try the next possible choice. If none of the choices lead to finding a whole word, we will return false. Okay, it's not a tongue twister, it's code. So what did they adjust? Okay, so they did a thing here. They're going through the offsets. So these offsets help us calculate the next thing we're evaluating, whether left, right. You can think of them as left, right, up, down. Okay. So we have the row offset, the column offset, looping through these 4 options, and now we check the results. If depth first search returns true, right, we're going to do something. But again, we're still constructing the solution. It's not yet done. So for now, we're just saying break, right, if it's true. And yeah, and we're using the word substring. So you can see we're using substring on the word. So the word is going to be reducing in size up until this terminating condition here, where it becomes 0. And then we actually found the whole word, the entire sequence of characters we're looking for, or the entire word we're looking for. Okay, let's keep going. Let's keep at it. So when the function is finished exploring all possible paths from the current cell and returns false, we revert the cell's original value to unmark it and allow it to be visited in other paths. This is important because if we don't reset the cell's value, it would still be marked as visited with an asterisk. An asterisk, I think is how you say it. Yeah, when we set it to the asterisk. So we have to set it back if it returns false. We have to revert it back to its original value to unmark it and allow it to be visited in other paths. So otherwise the search will be incomplete, right, or miss out on other possible paths. Because what if you're going from top to down and you see the asterisk, but then from down going up, that asterisk would have done what we wanted. Yeah. So let's look at where they do that here. I think they should highlight it. Yeah, there we go. So this will revert it back to the original value of the cell. So if there is no result, console log, and then while we are still in this depth first search, this particular instance of depth first search, where we have not returned something, actually no, whether we're returning or not, it looks like we're setting it back to what it was regardless, because the result is going to be true or false. So there's that. In summary, this is what the code looks like. This is our function. We pass in a grid and the word. We get the grid length, we get the height, right, by checking the length of a single column. And then, or actually this is the width, right, this is the height. And we loop through, loop inside a loop, and call depth first search. And then if that ever returns true, finally, we return true. Yes, we have the word. Otherwise, we say false. And this is our recursive function. You can see where we're calling it again. We're calling it again in here for each offset. So we have offsets right, top, actually no, bottom, right, top, and left, like so. Because this is X, this is Y, basically. And Y goes downwards. So from 0 down. 0 is up, right, and it goes down. It increases as you go down. So we're looping through that, and this is the terminating condition for our recursion if we're done with the length. And because the word length is being adjusted every time we call this function with this substring, so it's shifting one character at a time with every recursive call. And basically we say, oh, if there's nowhere to go, basically when we add b's in our recursive call. If there's nowhere to go, just return false. So if we're at the edge and we want that to go left, right, this is going to trigger. If we're at the right and we want it to go right, the rightmost side and we want that to go right, this is going to trigger. If we're at the topmost row and we want it to go even higher, this would trigger. And if we are at the bottom and want it to go lower, this would trigger. And then if we did succeed in going wherever it is we wanted to go, but the words don't match, it's still going to return false. And then basically defaults false for the result. We mark it, oh, we've seen this, right? It's not false so far. We've not returned false so far, and we've seen this. So now let's call it again, basically. And if we have a result that is true, if result is modified to true at some point, just break out of this. Don't check other things. And then when we're done, we return the results. This part is a bit slightly loose end in my mind, but I mean, we can step through the code later. The point of the video is to get a general idea of the intuition behind all of these steps. And with that, we're done, really. There's not much else to do over here. So yeah, so there is to it. At what point does this thing oh yes, if we reach the end, then it returns true. Okay, so it returns false here, and then down the line it would just break out of checking in here. I think that's it. Not 100% sure. You can step through the code later with the debugger with a bunch of examples. There are a bunch of examples here you can run the code with. Feel free to do that. Feel free to do that your own time. Time for this video is up. So let's look through the time complexity. So that's some wild time complexity, whatever. Let's look at the space complexity. O of L is the length of the words we searched in the grid. Okay, the length of the words we searched in the grid is what determines how the space we require for the solution grows. And it's the maximum depth of the recursive call tree at any point during the search. So it's time complexity. In the depth first search function, we initially have 4 directions to explore. However, there are only 3 choices left in each cell afterward because one has already been explored. Okay. Okay, you can only typically you're coming from somewhere already, and you can only go the other 3 directions because where you're coming from has already been explored. Okay, that makes sense. And the time complexity of the algorithm would be n times n. That's the what is n? 3l. L is the number of words we're looking for, but n is the number of cells. Okay, number of cells in the total number of cells in the grid, which does make sense. Okay. And actually, no. If we check our algorithm, n is, yeah, the grid length. So that's, n represents rows. Okay, the number of rows in this cell. I guess that makes sense. And actually, that should be columns. But it grows linearly with the number of cells in the operation, and L is the length of the word we're searching for. Okay. So 3 to the power L, n times 3 to the power L. When you're doing recursion, time complexity stuff tends to be super complex. So it's more of like almost a memory thing, right? Because you probably won't have the intuition in an interview and atmosphere of stress and all to figure it out. But this video has gone on too long. That's all about this. Code in the description. Check it out. See you next time. Ciao.